Well, thanks for inviting me. This is not a topic I've talked on for many, many years. But at any rate, and let me say at the beginning, please ask questions. You know, speaking to a general audience like this, in some sense, I don't have any idea what you do or don't know, and so on. So, please, let me have it, so to speak. Let me see what we got here. See which one of these does what. Oh, there we go. Okay, so this is, for this talk, I'm just going to give you some idea about what the general idea is for growing crystals by this technique, make comments about how one goes about choosing a particular flux if you have some particular crystal in mind that you'd like to do. Containers is a big deal because a lot of fluxes will eat your container if you're not careful about it. Then getting the crystals out from the melt is also an issue because sometimes, for instance, originally when I was doing this kind of stuff, a lot of what you did was chemical leaching, and often the stuff that you want is less robust than the flux you have it in chemically, so that can be a trick. And then along the way, I thought I would just give you some examples of the kind of things one runs across when you try to use this technique. But overall, the thing about growing crystals from metallic fluxes is that it's a really what you might call a low-rent operation. It doesn't take much equipment to do it. You can get really good materials by doing this, and there's always an advantage to growing your own stuff. I mean, you know what it is, you know how to fool around with it, how to change things in the growth conditions, and so on. And of course, these days, one can do so much, even with small single crystals, that, that when I was a PhD student years ago, my PhD advisor almost never worked with single crystals, and now it's everybody does it. Okay, so of course the first thing if you're going to fool around in materials is that learn the periodic table so that it's your good friend. It's not so, maybe everybody these days knows the periodic table. I don't know. Do students know everything?
They still don't know the length of the length.
Well, that's right. But which one of these guys is the laser? Oh, there we go. Let me go back. The typical fluxes one uses are these tend to be these low melting elements in here. Especially aluminum, gallium, indium, tin, antimony, bismuth, lead, so on, even thallium, so on. But there's also mixtures in here where certain alloy mixtures actually have rather low eutectic temperatures, and they're actually quite good. And one of the difficulties you run in with trying to grow certain kinds of materials is that certain elements form such stable compounds with everything that they either have very low solubilities or you get out materials that you're not interested in. So learn the table. It's good for you. Now I have this chart that Priscilla Rosa gave me about how are crystals synthesized, and there's just many different ways to make crystals, all kinds, and different techniques are good for different things. And we're in this, if you say, this very limited subgroup of techniques, solution growth, and flux growth is essentially one aspect of this. So, everybody knows about rock candy, and so there's probably, and there's nothing about the growth of crystals, single crystals from metallic fluxes that differs really from growing rock candy. It's essentially, you have a melt that at some point some ingredients can precipitate out from it as you reduce the temperature. And in doing this, this is just an example of sucrose dissolved in water. The difference in solubilities between, say, room temperature and the boiling point of water is a large factor, and so you can grow very easily these rock candy. A way to do it better, of course, is that you do some preliminary cooling down, separate out some small crystallites and use them as seeds. In other words, you can use a seed to go back in and use that to nucleate larger crystals. And a lot of the work that goes on in growing from metallic fluxes is that almost nobody uses seeds in this technique. In fact, you just use a spontaneous nucleation as you're cooling down these metallic melts. But I don't see any reason why you shouldn't be able to do seeded growths, and in fact you might be able to do it by cycling. In other words, you precipitate out some crystals, and then you could reheat your melt to redissolve and perhaps get bigger crystals that way. But nobody I know does that, actually. Usually you get from the growths I'm going to talk about, you often get crystals that are plenty big to work with. There's another aspect here that I can comment on. You see, when you have sucrose precipitating from water, there's always the question that shows up in the growths of whether you incorporate parts of the flux into your crystals that you might not think would be there. And to give you an example of this kind of thing, if you look at a shaker of salt, you look at it, you have very small crystals of sodium chloride, right? Sodium chloride salt comes from these salt evaporation processes. If you prepare salt that's hydroxyl free, in other words, you can make salt by just reacting it from sodium and chlorine with no water present. You actually get completely different properties in the sense that, in mechanical properties, in the sense that salt, it spreads like butter if you make it that way. And the reason, apparently, for this is that some hydroxyl at low level, OH minus, gets incorporated into the crystals in place of the chlorine. So that's always, low levels of impurities can actually have a big effect on what's going on. So let's start with a very simple phase diagram. There was a talk earlier this week on phase diagrams, so everybody's an expert on phase diagrams. So here's something simple: aluminum, silicon. It's a simple eutectic system. There's essentially no very low solubility of aluminum in silicon. Over here you don't, it's not indicated that there's any solubility of aluminum in silicon, and the amount of silicon that will dissolve in aluminum here is fairly small. You have this eutectic here, and so then in fact you could grow silicon crystals out of aluminum by just starting with a melt composition over here somewhere, cooling down. And what this phase diagram means is, for example, if you're at 20 atomic percent, you come down that there's somewhere around 800 centigrade, you'll start precipitating out silicon. And then, so in order to do a growth of this kind, you need some kind of crucible to hold this in. So the typical, so let me comment on the more general examples here of, and we also, there's a couple of papers that I was involved with, just talks about these general, the general topic that I'm talking about here. But for instance, here's the phase diagram of lanthanum tin, and for example, if you wanted to grow lanthanum tin 3 material, you could go with melts over in this range here, and or also cerium tin 3, which is another copper 3 gold type structure. Go with melts over here. And so what sets for these simple cases where you're actually using all the ingredients of the melt in order to produce the crystals, what you need to do here is so pick a crucible material, and the standard kind of crucible material that you would use for something like this is aluminum oxide, Al2O3. And one of the, it has a couple of nice advantages. Al2O3 can be gotten in high purity crucibles, and a standard group that you get it from is Coors Beer Company. They have a ceramics division because they use aluminum oxide for filtering their beers, you know, and it's fairly high density, and it's quite inert. And you might say that, for instance, pure lanthanum melt. If you melt lanthanum in aluminum oxide, it will eat the crucible. And it eats the crucible. Lanthanum oxides are extremely stable. But when it's dissolved in tin, the activity of lanthanum goes way down, and and so that you get very little crucible attack. The standard, but of course, this kind of melt is very reactive in air. Tin is reactive in air. Lanthanum is reactive in air. So you need to have some kind of a cover, meaning inert atmosphere, for it to be in. And the standard way to do that is to seal whatever your crucible and with its materials into, say, a quartz glass tube. Quartz glass can be operated, can be used up to about 1200 centigrade. Above 1200 centigrade, it so-called devitrifies. It starts to crystallize, and you can use it at slightly higher temperatures than 1200 if you adjust the pressure in the tube when you seal it off. And and the other thing to say is it takes a little experience to get used to working with quartz. It's so you usually use an oxyhydrogen torch to seal it off, although you can do it with acetylene, or people do it with other things, but oxyhydrogen works quite well. What you learn about quartz is that it has effectively zero coefficient of thermal expansion. So what does that mean? That means that, well, it means that you can take hot quartz and stick it in water, and it won't break. But the other thing is that if you have a crucible that you place into a quartz tube, when you heat it up, that, for instance, aluminum oxide crucible has a much greater thermal expansion than quartz. And so if the crucible's contacting the bottom of the tube, when it heats up, it's going to break the tube. And so you have to set things up either to somehow lift put something in there to lift the crucible off the bottom of your quartz tube. Or the simpler way is you take the quartz tube, you start out with quartz, you seal it, and then it's a somewhat pointed business. You heat it, the end of it in a torch, and you can just take it and press it onto, say, a copper hearth or something, or some piece of metal, and just flatten the bottom out so that the crucible will go down and sit without touching the sides. Important to do that. There's one other thing that this is just a side remark that about aluminum oxide. Even though it has what's called very good thermal shock resistance, meaning that you can heat it up quite fast and it won't break, there are some times when you have ingredients in your crucible that react as you're heating them up, that in such an exothermic way that they will break your crucible. And an example of that is if you take, say, lanthanum metal with platinum, for example. Lanthanum, platinum, when if you put them, try it sometime, put a little bit of platinum and lanthanum in a crucible and, in an inert atmosphere or in a vacuum. Heat it up and watch when it starts to react. Lights up just like a light bulb. It just goes, and that's enough to crack your crucible. And so the way you get around that, if you will, is if you're trying to grow things in a flux. I mean, for instance, you might say, well, gee, maybe I can grow a lanthanum platinum compound in molten tin, rather than trying to make lanthanum tin 3. Tin melts at a rather low temperature compared to lanthanum and platinum, and the reaction that this very exothermic reaction happens at some temperature that's maybe around 1,000 degrees or so. If you heat up slowly enough, the tin can dissolve these elements before they get together to react in this very exothermic way. So just something to keep in mind. Okay, so here's a picture of how you might how we often do things, and so this is sort of an example of growing a cerium, rhodium, indium from using cerium, rhodium in excess indium, and so this is what is just the elements, cerium, indium, and rhodium in an alumina crucible. And the setup here is that you put this is your quartz tube, you load your crucible, you put it into your quartz tube. Here it's being set off by probably more Quartz Wall. I'll comment more about Quartz Wall in a minute. And then you seal it, and then you neck the tube down at the end to, working with quartz, as I say, is just something you learn how to do. So let me comment about this particular compound here. There's a set of cerium noble metal, if you will, compounds of formula like cerium, rhodium 2, cerium iron 2, cerium platinum 2. They're so-called cubic lattice phases, and I'll talk a little bit more about what they are. But and there's a kind of crazy old notation that you'll run across if you work with these things. They're called C15s. And it has to do with a crystallographic designation from the old days. There's a number of, they were elemental crystal structures were started with the letter A, A1, A2, like face center cubic, body center cubic, and things like that. And there's early days in when I was growing up was called high TC, which was 17 degrees for superconductivity. all the compounds that had the highest TCs then were A15 crystal structure. And the A15 crystal structure, in fact, is not an elemental crystal structure, but it was believed to be a crystal structure of elemental tungsten, which turned out to be tungsten 3 oxygen. But C15 was one of the compounds, these lattice phases, in this cubic lattice phase. So this particular research field in condensed matter got going in a particular way when I was trying to grow cerium lattice phases out of indium. And it turned out it didn't work. And what I got was I tried cerium rhodium, and I got, instead of cerium rhodium, I got some crystals which were not cubic. They were cerium rhodium indium 5. And the particular properties that these compounds had, that's antiferromagnet at about a little over 3 Kelvin. And there's very little entropy evolved by the time in specific heat by the antiferromagnetic transition temperature. It's about 1/3 of R log 2. And so this led to some studies that were under pressure, which led to finding superconductivity in this particular compound. The thing that was curious here was that cerium rhodium indium 5 and cerium iridium indium 5 grew very easily from initially from the indium flux. Cerium cobalt, so in your periodic table, the cobalt column is cobalt, rhodium, iridium. And so the question was, why didn't cerium cobalt indium 5, why wasn't that coming out also? Well, it turns out that, which proved to be actually in many ways the most interesting compound in the group, but the cerium cobalt didn't come out because we weren't taking the melts to low enough temperature. It turns out that cerium and cobalt tend, if you look at the cerium cobalt phase diagram, there's a very deep eutectic which you can use that's somewhere around cerium 3 cobalt that actually you can use as a flux for growing certain other compounds. And it's also easy to get rid of chemically, turns out. But when we took it, when Chadimir Petrovic took the melts to much lower temperatures, he managed to get these other things. So sometimes it's you get fooled. How do you say? By not cooling far enough. But let me go a little further into what's really going on in a tube like this. You can with indium, you can get rid of indium fairly easily with dilute hydrochloric acid. And a lot of intermetallic compounds would be stable against dilute hydrochloric acid, so you could get rid of the flux without getting rid of the crystals. However, that it also had turned out that that you can actually get some stuff that's called Quartz Wall, and you can actually, you can take, if you put Quartz Wall on top of your crucible, you can you can remove the growth from some temperature cycle like this, while the indium is still molten, and indium melts at, say, 156 centigrade, something like that. So you can take this out of the furnace, say, at 200 centigrade, and you can actually put it into a centrifuge, just a little chemical centrifuge here, upside down, and spin it up while it's still warm. And amazingly enough, that the flux will shoot through the quartz wall and leave the crystals behind. And so you can do this with many things. perhaps disadvantage, well, a thing to consider when doing this is that the quartz wool, this is SiO2, the quartz wool, when you put it in, there's always a little bit of dust that comes down from it, so you'll have some SiO2 into the melt, which can act as nucleation sites, but it can also be a source of silicon into the system. So another way to do this process would be to not use the quartz wool, cool the flux all the way down to freezing, through freezing, and then reload the crucible with quartz wool afterwards, and then spin it out separately after you've done the original growth cycle. Well, here's a list of possible containers, and I'll say a little bit more at the end about which containers one can use. For instance, one of the for certain material, I mean, indium is a nice material to grow crystals from. And also, for instance, indium does not attack tantalum, and so you can actually go to temperatures. For instance, if you want to go to temperatures much higher than 1200, you can seal them in a tantalum tube. You can do this in an arc furnace, and then put the tantalum in an inert atmosphere environment in a say a furnace that goes to 15 or 1600, something like that. And materials that people have studied at some length that you can grow from indium like that are like ytterbium, rhodium-2 silicon-2, which Steglich and company have done an enormous amount of work on, but also the crazy hidden order material, uranium, ruthenium-2 silicon-2, you can grow from very high. But you have to go to quite high temperatures because these are very stable intermetallics, which, and so that they don't have high solubility in the flux, so you go to much higher temperatures. The furnaces, and also to say that, this is looking at the inside of a box furnace here. This is like a silicon carbide furnace. These are silicon carbide rods. Silicon carbide furnaces operate up to about 1500 centigrade. If you operate close to, these are fine for these kind of quartz operations to 1200. The lifetime of these elements, which actually aren't so cheap, is greatly reduced if you work near 1500, and a lot of the high temperature furnaces now use molybdisilicide elements, which last longer and actually can go to higher temperatures. Nobody's asking any questions. Too early? Okay.
Ask them questions.
Okay, so let me talk about, for instance, this interesting material that we're going to have a workshop on tomorrow, samarium hexafluoride. So the hexafluorides are a beautiful, really simple cubic crystal structure, which actually you can grow from aluminum. But you can see, for instance, here's a phase diagram of aluminum and boron. And you can see that boron, the solubility of boron in liquid aluminum is actually quite low. It also turns out that these rare earth hexafluorides are extremely stable compounds. And the more stable, or as they say, more refractory a compound is, usually the lower its solubility. And so in order to grow samarium B6 from this kind of melt, you actually have to go to fairly high temperatures, usually in a silicon carbide furnace, go to about close to 1500, maybe 1450, which how do you say, gives you more lifetime for your furnace elements. But then you have to do this under a cover because you can't encapsulate the crucibles in quartz to work at those temperatures. But you can etch the crystals out from sodium hydroxide with using sodium hydroxide, which does not attack those particular crystals. The arrangement that a kind of arrangement that one uses to do this is to take a tube furnace and turn it on end and hang the crucible inside a ceramic tube that you have inert gas in. In other words, here's your high temperature tube furnace with a typically mullite or aluminum oxide ceramic tube. You can also stack crucibles in the bottom here up to somewhere in the middle of the tube and put your melt in there. And typically when one does these kinds of runs, you stack, you load the number of loaded crucibles for flux growth. You typically fit with 3-4 crucibles into this furnace. So then, as I say, you cool all the way down to low temperatures. You go up to 1500, soak it, cool it down. Typical ramp speeds anywhere from a few degrees an hour to 10 or 15 degrees an hour, depending on what you're trying to do, and then leaching it out in the end. And these days, there's always this particular problem of getting rid of the leaching solution when you're done, which is a chemical waste problem. It's its own business.
Can I ask you questions then?
Yeah.
Is there, other than geometry, is there a reason for putting the tube furnace vertical for that rope?
And I'll address it right here. That's because, okay, so what's a typical growth parameters? You can get, say, 50, the typical size of aluminum crucibles that you can buy from Coors or McDaniel or somebody like that are 2 ml, 5 ml, and 50 ml. And for simple things, simple exploration, 2 ml crucibles are great. But the solubility of B6 in molten aluminum, and you can do this by preparing by other techniques. Well, I did it originally with lanthanum B6. You can arc melt lanthanum B6. Samarium's a problem. It has a high vapor pressure, which is so working with an arc furnace is a bit of a nuisance. But I took lanthanum B6, made it, and heated it up in actually an aluminum crucible with some aluminum and let it sit at 1200 degrees for a while to see how much the weight of the pill of lanthanum B6 changed. And it seemed, as I remember, 13.6 milligrams is what I remember from the old days of lanthanum B6 are soluble in 1 gram of aluminum at 1200 degrees. So the typical growth for these hexafluorides is that you have a crucible of order of 50 ml crucible that in which you put between 50 and 70 grams of aluminum, and the total SMB6 amount here is something of order 600, less than a gram, 600 milligrams, maybe something like that. But you see here is a holder for holding a set of crucibles, and made out of, this was from just machined out of graphite and then outgassed, because graphite tends to have a lot of crud in it. And then this can fit into a horizontal tube furnace. And so the reason for going vertical was that you couldn't stack the average 50 ml crucible into easily into a tube. But if you have a large enough bore tube furnace, you can do it. And this is an example from Priscilla Rosa at Los Alamos. And so this is about a 3-inch tube here. It turns out that it has these supports on the end. If you don't do this, there's a real problem with thermal sag if you go to high temperatures. The idea with this molybdenum furnace is that you can go to temperatures comfortably above 1500 degrees. You know, I mean, these things, so you can work them up at least to 1650. There's another problem that happened at those temperatures with aluminum. There's some point at which aluminum oxide starts to dissolve in aluminum, and there's a couple of things that happen when that. One is that the vapor pressure of you start getting aluminum when you melt it always has a small cover of Al2O3 on it, no matter what you do, right? When you get rid of that, the vapor pressure of aluminum starts to cause you problems. I mean, you can, if you're growing in quartz, you're already at 1200 degrees or close to 1200. If you aluminum vapor will start attacking quartz, and so the growths that you can do with aluminum, you sort of have to abbreviate them. You don't stay there too long, because what the attack does, it devitrifies the tube, and you'll lose the tube. In other words, you'll lose your inert situation. The other thing is that when aluminum oxide dissolves in aluminum, that aluminum oxide itself can crystallize out and it forms sapphires. And I did a lot of early growths in aluminum in using RF furnace. In other words, an RF furnace, which you have an RF coil with a crucible in it, and then a tube that is in which you can have either a vacuum or an inert gas. And one advantage of that kind of situation is it's fast, and you can actually go to quite high temperatures. But I found when I got to temperatures up around 1600, 1650, that not only did you get quite a bit of aluminum vapor coming off, but when you cooled it down, you shut the RF off and took it out, and you grab the crucible, it's like grabbing a pincushion, because all these sapphire crystals start growing out from the aluminum crucible. So if you have a nice RF furnace to do that kind of stuff, just be careful when you take the thing out at the end of the day. As I said here, with this particular furnace that Priscilla had, where you could load it in very nicely horizontally, really works well. And you have end caps here that with these fans to keep the ends of the tube cold, and this is there's O-ring type seals here, which and then here's like your argon bottle, for example, in here. The other thing that you can do, again, here's like a holder out here, that you can even with high purity argon, ultra high purity argon, it still has reactive gases in there at some level. And if so, you try to keep your gas flow through there slow, but and to to do these kind of runs, one often pumps out the tube first, then fills it and has a very slow flow rate. But you can put a getter crucible in the front stream here, just say pure aluminum, something like that, to getter the gas that goes in. You can also get, you know, they sell fancy gas purification trains where, or you can make such a thing. You can pass your gas over various heated metals to remove traces of water, vapor, oxygen, and so on that can be left in there. Okay. So let me give some examples of fooling around with various growths. Here's a paper that showed up in 1988 from Noack and Fellner on this compound, and this is a cubic lattice phase. And so the general formula for the cubic C15 lattice phase is AB2. So it would be like ytterbium, you know, the last rare earth. This compound would be ytterbium copper 2, and he was substituting part of the copper. So what's the deal with this crystal structure? The rare earth atom in this crystal structure is on what's called a diamond lattice. And everybody here knows what a diamond lattice is, right? It's two FCC lattices displaced by a quarter of body diagonal. It's cubic, and so that each atom on that lattice is 4 coordinated. Like this guy is at a quarter, and it's got these four face-centered sites around it. Okay, so the AB2 structure should actually be considered A2B4, the A2 being on a diamond lattice. So this compound, and so what's interesting about this compound, this is a resistant, is cooling it down to low temperatures, and what they find is that there's some drop in resistivity out here at 50 Kelvin, and they figure out that this actually appears to be a valence change. And these kind of valence changes, to find nice example of the example in rare earths that has been of interest since I don't know, the 1950s, maybe the 1940s, is elemental cerium, which has a volume collapse, which has to do with the cerium, whether the cerium F electron is delocalized or not, or that's one way of describing it. And how do you think about that? If you have an F electron inside the atom, what it does, I mean, all of the simplest stuff about rare earth chemistry is that they're chemically, with a few exceptions, all highly similar. And why is that? It's because the F is an inner electron. It shields, you increase the nuclear charge by 1. The F electron comes in and it effectively shields that nuclear charge, right? And so chemically, the stuff doesn't look any different than the element before it, because the outer electrons that are doing essentially all the valence chemistry are the same. But the shielding's not perfect, so there's a lanthanum contraction. So the metallic radius changes from 1.85 at lanthanum to, 1.7 something out at lutetium. but they're all chemically very similar, and that's of course why it's wonderful to work with the rare earths, because you can substitute one for the other and so on, and do all kinds of comparative experiments. But when this work came out, it occurred to me I'd done some work with these lattice phases, and as I say, the rare earth, in other words, the ytterbium plus indium, there are these two face-centered cubic lattices, and if you make and so that you could put a different atom, perhaps, on one of those cubic lattices. And so the idea that I had, which I think Fellner and Noack didn't realize, is that they were getting preferential substitution on one of these FCC lattices in this particular structure. And so that the composition that you would like to make it at would be YbInCu4. So this is actually what this structure really is. Here's where all the coppers are in this structure. And so we tried growing single crystals, and it turned out that so I made an indium copper flux and put a terbium in it, and instead of having a 10 or 20 degree spread in the transition width, that we got these crystals that had a transition width of 1 or 2 degrees. And it turned out that, but it was not that the indium copper ratio in there was 1 to 4 or whatever, you know. It turned out that I was careless, and the ratio that I did was at 1 to 1, and this is what came out. And a friend of mine in Frankfurt, Bruno Luthi, was interested in doing elastic measurements on this stuff, and he had a very good crystal chemist working with him, a guy called Asmuth. Asmuth went through the entire ytterbium, indium, copper phase diagram to see where you could grow this stuff and come out with essentially this perfect stoichiometric stuff. And it turned out it was just 1 to 1. It was just a complete piece of luck, you know, that it happened that way. But it turned out that and someone was able to study this volume collapse, which is not a common situation. So it was actually a very nice system to work with. What happens? There's just a comment here. Is there different? Because it's this volume collapse, it turns to damage the crystals when you go through the transition. So when you cycle it, the resistance ratio changes significantly, and so you have to anneal and do things like that. And I'll comment a little bit more on annealing in a minute. You see, I'm about to run out of time here. I wanted to. One of the original heavy fermion compound was something called cerium aluminum 3, and it's and here it is inside here. This is cerium aluminum 3, and so you look at this and you say, you know, how can you possibly grow single crystals of this? Well, it turns out this is what you call buried in there, and there's no simple way to do it, and the only single crystals I know of that anybody got were done by strain annealing of an arc melt of this stuff, and the way that strain annealing works is you you can distort something, or even just arc melting, and the cool down, puts strains in, and then you can sit somewhere under the melting point in here and anneal things in. I mean, for example, just as for instance, pure rare earth elements, almost all of them, they're hexagonal or some form of hexagonal, double hexagonal, but they go through a cubic phase at high temperatures, right? So if you take a rare earth and you want a single crystal of the hexagonal phase, you can arc melt it and then anneal it, say, at 1200 degrees in a quartz tube wrapped in tantalum foil to keep it from reacting with a quartz tube. So I was interested in resistance measurements once on rare earths. So I took some 3/9 lanthanum and annealed it, and just from arc melting it. Arc melted a big pill, annealed it, took it out, and you could look at it and you could see it was 3 crystals. I mean, it was just, there were 3 domains in there. And so you could get 4/9 lanthanum from, I can't remember who I got that from. I got 4/9 lanthanum and did it, and I annealed it same way, 1 single crystal. So it makes a difference, that kind of stuff. Well, anyhow, here's this cerium aluminum 3. It has what's called the DO19 structure. And DO19 is, again, this crazy old-fashioned nomenclature. It's the hexagonal stacking of copper 3 gold. Copper 3 gold is an FCC lattice with copper at the face centers and gold at the body corners, okay? You can imagine, just as you have hexagonal and cubic stackings of various layers, you can take the layers in there and stack them hexagonally. Then you get to DO19. Well, it turned out that there was a compound, uranium platinum 3, that also had the DO19 structure. And its properties in the early 80s weren't particularly well known. And I heard from a friend of mine that from Oregon, a guy called Al Arco, that they'd actually managed to grow some uranium compounds using molten bismuth. And so the idea, here's a uranium bismuth phase diagram. And you can see in here that there's a lot of solubility of uranium out here in molten bismuth. And so I thought, well, gee, maybe I can grow uranium platinum 3 out of bismuth. And I tried it, and sure enough, you got these beautiful needles of hexagonal stuff. And we cooled it down, and they had a very high resistance ratio, this stuff. And I thought, gee, maybe we can do the Hosfin-Alphin on this material. Because it was way over, it was a few hundred, the resistance ratio of this material. But when we cooled it down, the stuff went superconducting, which was not expected at the time. At 0.5 degrees, it turns out that not as good resistance ratio material had a lower TC. But here's what the specific heat looked like going through there, just checking to see if it's a bulk superconducting transition. And we tried to get this published in Phys Rev Letters, which we did eventually, but the referees didn't didn't think this was a very good specific heat anomaly. Too broad, they thought it was kind of lousy. And take a guess what's going on there. No? Yeah, that's a good guess, though. Yeah, no. Two transitions. This is maybe the first example of that. I don't know. But it took a while to figure that out, but... Huh? But,
The audience is too young.
Yeah, that's right. Yeah, it's a very unusual, still somewhat mysterious phase, but they allowed us to publish it. It wasn't until a number of years later that it was figured out that there were actually two separate superconducting transitions in there. which is what you say is the marker of, one of the markers of very unusual superconductivity. And then there's this other heavy fermion superconductor that we worked with, which was uranium beryllium-13. Now uranium beryllium-13 is, that turns out that, and so the question was, can we grow, you can see here, you can get a lot of aluminum into, a lot of uranium into molten aluminum here. I mean, you can go out, 10-15%, and typically you're running at, of order 5% stuff that you want to grow out of these phase diagrams. And there are no compounds between aluminum and beryllium. And so superconductivity had been seen in this cubic compound, uranium beryllium-13, by a guy called Ernst Bucher. And he, at Bell Labs at the time. And what he found was there's a superconducting transition around 0.9 Kelvin in arc melted material. And in, but that the critical field was enormously high. And so he thought it was filamentary superconductivity, which if there are filaments, the field doesn't, in some sense, penetrates through the whole material, and would give you that. And so he couldn't believe that you would have a critical field of that high for something that had a TC of 0.9 Kelvin. And so when the heavy fermion superconductivity was discovered in serum copper-2 silicon, to Hans Rudyard said, well, gee, maybe we should try uranium beryllium-13 again, but nobody will believe it unless we grow single crystals. And so I was working at Los Alamos at the time, and I figured you needed a beryllium crucible to do this job, because beryllium oxide is exceedingly stable, and I figured if you had beryllium in an aluminum melt, it would attack an aluminum crucible. And the other problem with beryllium is that it's, I'm just about running out of time here, but is that beryllium, you have to be very careful when you're working with it. Beryllium oxide, for people that are sensitive to it, they're sensitive at the ppm level, meaning that you're just breathing the dust. It's beryllium oxide moist. That's extremely dangerous. And you can do a skin test to find out if you're sensitive or not, or work in a beryllium facility. I was working at Los Alamos in those days, and they had facilities to work on anything, almost. So at any rate, I was trying to grow, and they also had a bunch of crucibles of all kind back in these cabinets. They had beryllium crucibles. And I kept trying these growths, and nothing would come out from them. Putting uranium and beryllium in these, in aluminum. And I didn't understand why. And I'm walking out one evening, and there's this old chemist, Clayton Olson, standing there, and he asked me what I was doing. And I said, yeah, I'm trying to grow these crystals, and I'm using beryllium crucibles. And he says to me, man, he says, those beryllium crucibles, he said, they're just like a sponge. They just soak up water. And I'm thinking, this is New Mexico, where the humidity is, 0.5% or something. And so I took one of these crucibles and I baked it out. And then I said, I'm going to try it once more. And then when I did the run, a crystal came out that was big enough in the bottom of the crucible, I could have made a brooch for my grandmother from the thing. I mean, it was, and but apart from but it turned out ultimately that you don't need to use a beryllium crucible. The beryllium dissolved in aluminum does not attack those crucibles, and so that was, something that was learned later. The other thing is, and this is germane to something that you should keep in mind when flux coring, that it turns out that aluminum can substitute on one of the beryllium sites. There are two beryllium sites in there, a 12 site and a 1 site. And then you tend to get aluminum, some aluminum substituting on that other site. This is, and I mean, this is something that you have to be aware of when doing flux growth. The other thing, I mean, I should have mentioned with the samarium hexaboride, when you grow thickish crystals, you tend to get lamella of aluminum coherently growing inside the crystals. It's not, there's no substitution of aluminum that we know of in these hexaborides, but you get these lamella in there that one has to be careful to either grind, essentially abrade out or take crystals that are small enough that don't have that. I can give another example. At one time I was trying to grow a cerium cobalt crystals from molten lead. And what came out from this cerium cobalt, and this was in an aluminum oxide crucible, I got a compound that turned out to be cerium 5, lead 3, oxygen. No cobalt in there at all. And the oxygen was just coming from the crucible. There it was. And these things are not so easy to find often. Okay, one other thing is just to sort of finish up, that sometimes various materials are very hard to make in the arc furnace. For instance, if you ever try to make iridium compound, iridium metal is melts at 2400 centigrade. So to make, say for instance, europium iridium 2, europium boils at 1500. So in an arc furnace, there's trouble. And when you arc melt them, it turns out you think you've got the compound made, allowing for all the boil off. And then you crack the pill you make open. It's like an egg. It's got this yolk inside that's pure iridium that hasn't reacted. And so I spent some time growing europium iridium 2 and other rare earth iridium 2s, actually using molten copper. And it turned out, and that's at a temperature, copper melts at 1060, something like that, centigrade. And so that's, at least for me, that's too high to do melt spin. And actually I had to take I did this stuff in an RF furnace, so I was taking I did it in, I used yttria crucibles, which are, it's reactive, but in tantalum, and or in an RF furnace. And you can eat out these cubic lattice phases, like EuIR2, is really stable in nitric acid, for example. And so you can just eat the copper away, and you're left with this stuff. And it turned out this was trivalent europium, which is you don't usually get in intermetallics, but copper turned out to be actually a pretty nice element to use for this purpose. Okay, so just to finish up with these are the melting points of various oxides that one deals with. Aluminum oxide around 2000. MgO crucibles one can often get, they're quite good. One generally stays away from beryllium just for health reasons. But there's also yttria and zirconia crucibles, which are yttria stabilized zirconia and so on, which are quite good. And here's a kind of a list of what you get away with. Again, the aluminum growth. If you do aluminum growth to 1200, that when you spin them, the problem is that they'll react with the quartz, and they'll also react with the quartz wall. But you can actually spin into You can spin them, but you can cap them with a second crucible, and so that you can spin back into another aluminum crucible, and so beat the problem there. So that's sort of some general thing. I hope you get the general idea. It's a lot of fun to grow crystals this way. It's easy, doesn't require lots of equipment, and actually, it's the fluxes have proven to be an interesting way to go searching for materials. Also, you know, sometimes you get all kinds of things you didn't expect out of them. So, thanks for listening.